September 15, 1940, 11:07 a.m. Fighter Command Headquarters, Bentley Priory, Uxbridge. Air Chief Marshal Hugh Dowding stood before a massive plotting table, watching as WAF officers pushed colored markers across a map of southern England. Each marker represented a formation of German aircraft, Heinkel bombers, Messerschmitt fighters, detected minutes earlier by invisible eyes scattered along the coast. The markers moved with unnatural precision, their positions updated every 60 seconds. Dowding's hand rested on the table edge, steady despite the magnitude of what he was witnessing. Above him, Luftwaffe commander Hermann Göring had committed every available aircraft to a single massive assault. Destroy Fighter Command, break British resistance, and open the door for Operation Sea Lion, the invasion of Britain. But Göring was fighting blind. His pilots flew toward targets they believed were undefended, their formations intact, their confidence absolute. They had no idea that every aircraft, every formation, every altitude change had been tracked since crossing the French coast. They didn't know that RAF fighters were already climbing to intercept, positioned with mathematical precision at optimal altitude and bearing. They couldn't have known because the technology tracking them wasn't supposed to exist. What Göring didn't understand, what German intelligence had failed to grasp despite 3 years of frantic investigation, was that Britain had weaponized physics itself. Not a death ray, not a particle beam, but something infinitely more practical. Radio waves that could see in darkness, through clouds, across hundreds of miles. The British called it RDF, Radio Direction Finding. Within 2 years, the Americans would give it a name that stuck: radar. The story begins not with radar, but with a death ray that couldn't work. January 1935, Air Ministry, London. Director of Scientific Research Harry Wimperis sat across from Robert Watson Watt, superintendent of the Radio Research Station at Slough. Wimperis had a problem that kept him awake at night. German rearmament was accelerating. The Luftwaffe, though officially non-existent under Versailles Treaty restrictions, was clearly being assembled in secret. British air defenses consisted primarily of sound detectors, massive concrete acoustic mirrors that could supposedly hear approaching bombers. They worked poorly in good weather and not at all in wind or rain. Detection range was perhaps 8 miles on a perfect day, giving defenders perhaps 4 minutes warning. Wimperis needed something better. He'd watched Harry Grindle Matthews demonstrate his supposed death ray in 1924, seen it fail to scale beyond laboratory tricks. But the demonstration had planted a question. If electromagnetic energy couldn't kill at distance, could it detect at distance? Watson Watt listened to the problem, then asked his assistant Arnold Wilkins to run calculations. The math was straightforward. Broadcasting radio waves and detecting reflections from metal objects was theoretically possible. Aircraft were large metal objects. The inverse square law worked both ways. A reflected signal would be weak, but modern receivers were sensitive. Wilkins spent 3 days working through the numbers, then delivered a 4-page memorandum titled Detection and Location of Aircraft by Radio Methods. The conclusion was conservative but definite. Detection of aircraft by radio reflection was feasible at ranges up to perhaps 50 miles, possibly more with better equipment. The required technology already existed. Radio transmitters, directional antennas, sensitive receivers, all standard equipment for broadcast and communication purposes. No new physics needed to be invented. It was engineering, not science fiction. On February 26, 1935, Watson Watt conducted the first demonstration. He had no time to build dedicated equipment. Instead, he used the BBC's shortwave transmitter at Daventry, which broadcast at 49 meters wavelength with 10 kilowatts of power. The experimental site was a field near Weedon, 8 miles from Daventry. Watson-Watt positioned a receiver van equipped with a cathode ray oscilloscope, an antenna oriented perpendicular to the transmitter, and Arnold Wilkins manning the controls. The RAF contributed a Handley Page Hayford, a biplane already obsolete but large and metal and available. At 11:30 a.m., the Hayford took off and flew a racetrack pattern. Wilkins watched the oscilloscope. The screen showed a continuous wave from the direct transmission. Then, as the bomber crossed the beam, a second signal appeared, flickering, weak but unmistakable. The aircraft was reflecting radio waves. The reflection was detectable. It worked. The Air Ministry allocated £10,000 for further research, by modern standards an absurdly small sum, roughly £700,000 in 2024 terms, to develop a technology that would determine national survival. But it was enough. Watson-Watt assembled a team at Orfordness, a desolate shingle spit on the Suffolk coast, and began building Britain's first radar station. The initial system was crude. A transmitter broadcasting at 25 meters wavelength, towers holding wire antennas, receivers tuned to detect the faintest reflections. Detection range crept upward, 10 miles, 20, 30. By June 1935, Watson-Watt's team could detect aircraft at 40 miles, far enough to give RAF fighters a fighting chance to intercept. But detection alone wasn't sufficient. The receivers picked up reflections, but determining exact position required triangulation. Watson-Watt developed a system using multiple receiving stations, each measuring the bearing of the reflected signal. Where the bearings intersected, the aircraft must be. The breakthrough came from Watson-Watt's realization that height mattered as much as position. By measuring the angle of the returning signal, operators could estimate not just location, but height. This was revolutionary. Sound detectors couldn't determine altitude at all. Radar could see in darkness, through clouds, and tell defenders exactly where the enemy was in three-dimensional space. By 1936, the system had evolved into Chain Home, Britain's radar network. The name was deliberately obscure. Secrecy was absolute. Workers building the stations knew only their specific tasks. Even RAF officers receiving radar information weren't told how it was generated. The first operational Chain Home station opened at Bodsey Manor in Suffolk in 1937. The installation was impossible to miss. 4 360-foot Spiel transmitter towers and 4 240-foot wooden receiver towers dominated the coastline. German intelligence photographed them repeatedly from the air, analyzed the structures, and concluded they were some form of communication system, possibly for ship-to-shore radio. The possibility that they were detection apparatus didn't register. German scientists working on their own radar research assumed the towers were far too tall for practical radio direction finding. The wavelength implied by the tower height, 10 to 13 meters, was considered unsuitable for detection work. This was Germany's critical error. British radar used long wavelengths deliberately. Shorter waves provided better accuracy but required more complex equipment and were more affected by weather. Watson-Watt's system traded precision for reliability. Chain Home couldn't pinpoint an aircraft to within yards, but it could detect formations at 100 miles and maintain tracking continuously. That was sufficient. By September 1938, during the Munich crisis, 5 Chain Home stations were operational, covering the Thames estuary and approaches to London. The network detected aircraft during crisis exercises, tracked them reliably, and provided fighter command with unprecedented warning time. The Air Ministry accelerated deployment. By April 1939, 20 Chain Home stations were operational, stretching from Southampton to the Firth of Forth. Each station could detect aircraft at ranges exceeding 100 miles. The stations were networked, their data flowing to fighter command headquarters via telephone lines. WAF operators plotted contacts on maps, calculating intercept vectors for RAF fighters. The system wasn't automated, everything was manual, plotted by hand, reported verbally, but it worked. Then Germany invaded Poland, and the defensive system Britain had spent 4 years building faced its first operational test. September 3, 1939, Britain declared war. Within hours, chain home stations detected aircraft approaching from the North Sea. The plots were relayed to Fighter Command. Fighters scrambled. The radar contacts proved to be RAF aircraft returning from patrol, not German bombers, but the system had responded exactly as designed. Britain could see enemies approaching long before they arrived. But radar was only half the battle. Detection meant nothing without fighters to intercept, and in 1939, Fighter Command faced a mathematical nightmare. Hugh Dowding understood the problem with brutal clarity. Britain couldn't afford to maintain standing patrols over every potential target. Fighters consumed fuel, pilots grew exhausted, and aircraft required maintenance. The Luftwaffe could choose when and where to attack. Fighter Command had to defend everywhere simultaneously. Radar transformed the equation. Instead of standing patrols, Dowding could keep fighters on the ground until raids were detected, then scramble them to intercept. The system Dowding developed was called the Dowding System, an integrated air defense network that combined radar detection, ground observer reports, radio communications, and fighter direction into a single coordinated response. It was revolutionary. No other nation had anything comparable. May 10, 1940, Germany invaded France. The RAF sent fighter squadrons to France as part of the British Expeditionary Force. These squadrons operated without radar coverage. The Luftwaffe achieved air superiority within days. Dowding, watching his fighters massacred over France, refused to commit additional squadrons. He needed them for the defense of Britain, where radar gave them a fighting chance. By June, France had fallen. Britain stood alone. German invasion barges assembled in French ports. The Luftwaffe, operating from captured airfields in France, was now within easy striking distance of London. Hitler issued Directive No. 16, Prepare for the Invasion of Britain. The operation, codenamed Sea Lion, required one prerequisite: air superiority over the English Channel and southern England. Goering assured Hitler that the Luftwaffe would destroy the RAF in 4 weeks. July 10, 1940, the Luftwaffe began preliminary operations, attacking coastal convoys, testing RAF response times. Chain Home detected every raid. Fighter Command scrambled interceptors, vectored them to their targets, and engaged the Germans with unsettling accuracy. Luftwaffe pilots reported that RAF fighters appeared at the worst possible moments, climbing through formations, attacking from altitude, positioned with precision that suggested the British knew exactly where the Germans would be. German intelligence struggled to explain this. Spies in Britain reported that radar stations existed, but didn't understand their purpose. Luftwaffe reconnaissance photographed the towers repeatedly but couldn't determine their function. The possibility that Britain had a comprehensive radar network tracking every aircraft seemed implausible. Goering dismissed radar as a factor. British fighters, he believed, were simply being used inefficiently. The RAF had inferior numbers, obsolete tactics, and would be destroyed through attrition. He ordered Alderdog, Eagle Day, a massive assault intended to overwhelm British defenses through sheer numbers. August 13, 1940, Alderdog commenced. The Luftwaffe launched 1,485 sorties, the largest aerial assault in history to that date. Chain Home detected the formations assembling over France. Fighter Command scrambled squadrons, directed them to intercept, and engaged the Germans across southern England. The Luftwaffe lost 45 aircraft. The RAF lost 13 fighters. Goering postponed further mass raids. But the Luftwaffe had learned something. The RAF fighters weren't distributed randomly. They appeared concentrated at specific points, suggesting centralized direction, and the British seemed particularly concerned about protecting certain locations, the tall towers along the coast. On August 12, one day before Adeltag, the Luftwaffe had attacked several radar stations, including Ventnor on the Isle of Wight. The raid damaged the station severely enough to take it offline for days. Fighter Command's detection capability in that sector degraded immediately. The Germans noticed. But Goering didn't follow up. Radar stations, he believed, were insignificant. Better to attack the airfields, destroy the fighters on the ground. This decision saved Britain. August 15, 1940. The Luftwaffe launched coordinated attacks from France, Belgium, Holland, Denmark, and Norway, every available airfield participating simultaneously. The assault involved 1,786 sorties. Chain-home detected formations assembling hours before they crossed the coast. Fighter Command had time to scramble, climb to altitude, and position at optimal intercept points. The battle raged from dawn to dusk. The Luftwaffe lost 75 aircraft. The RAF lost 34 fighters. Goering's plan to overwhelm British defenses through mass attacks had failed. The Germans didn't understand why. Luftwaffe intelligence estimated Fighter Command had perhaps 300 operational fighters remaining. In fact, Britain had over 700, with production exceeding losses. German bombers flew into concentrated defensive fire at locations where fighters shouldn't have been. Pilots reported RAF squadrons appearing from nowhere, perfectly positioned, as if the British could see through clouds. They could. Radar was tracking everything. At the heart of the system were the filter rooms. Located at Bentley Priory and regional centers, these rooms received raw radar plots from chain home stations and ground observer reports from the Royal Observer Corps. Operators wearing headsets listened to constant updates, bearing, range, altitude, estimated strength. They placed markers on plotting tables representing each contact. As new reports arrived, they moved the markers, tracking the raids in real time. The filtering process required judgment. Operators compared reports, assessed confidence levels, and eliminated impossibilities. The filtered tracks went to operations rooms, where controllers faced a different problem: resource allocation. Fighter Command had roughly 50 squadrons available. Every squadron scrambled meant fighters unavailable for subsequent raids. Controllers had to assess threat levels, predict attack routes, and commit fighters with incomplete information and no time for reconsideration. This system, detection, filtering, assessment, direction, gave Fighter Command a decisive advantage. German formations weren't just detected, they were tracked continuously from takeoff to return. Their altitude, heading, speed, and estimated size were known before they crossed the coast. RAF fighters scrambled with time to climb, positioned with fuel to fight, and directed to intercepts with mathematical precision. The Germans had nothing comparable. Luftwaffe formations assembled over France using timed coordination and visual signals. Controllers on the ground had no way to track aircraft once airborne. RAF fighters, directed by radio from ground controllers watching radar plots, had omniscient guidance. German pilots fought blind. The quantitative impact was devastating. In August 1940, the Luftwaffe flew 4,779 sorties and lost 774 aircraft, a loss rate of 16.2%. Fighter Command flew 5,864 sorties and lost 303 fighters, a loss rate of 5.1%. The Germans were losing 3 aircraft for every British fighter destroyed. By late August, the Luftwaffe had shifted tactics, attacking RAF airfields relentlessly. Radar detected the raids approaching, but once the Germans reached the coast, tracking degraded. Airfields were damaged. Fighter production couldn't match losses. Pilot exhaustion became critical. Dowding calculated that within 2 weeks, Fighter Command would be combat ineffective. Then Goering made his second catastrophic error. On September 7, 1940, frustrated by the RAF's refusal to collapse, Goering switched targets from airfields to London. The decision was partly retaliatory, but primarily strategic. Goering believed destroying London would force the RAF to commit its remaining fighters to a decisive battle over the capital, where the Luftwaffe's superior numbers would crush them. This shift saved Fighter Command. The attacks on airfields ceased, damaged stations were repaired, fighter strength stabilized, and the Luftwaffe, concentrated against a single target, became predictable. Chain-home detected formations assembling over France every afternoon, vectors pointing toward London. September 15, 1940, Goering committed his remaining reserves to 2 massive raids against London. The first wave launched at 11 a.m., over 200 bombers escorted by 400 fighters. Chain-home detected them at extreme range. Fighter Command scrambled every available squadron, positioning them in layers. The Germans encountered resistance they didn't expect, fighters attacking from multiple directions, coordinated with precision. The first raid retreated. The second wave launched at 2 p.m. Again, Chain-home detected them assembling. Again, Fighter Command scrambled, positioned, and intercepted. The battles lasted hours. The Luftwaffe lost 60 aircraft. The RAF lost 34 fighters. Goering's plan to overwhelm British defenses through mass attacks had failed. 2 days later, Hitler postponed Operation Sea Lion indefinitely. The invasion of Britain was cancelled. The Battle of Britain was over. But the story of radar's victory is incomplete without examining what made Chain-home work, not the technology itself, but the infrastructure and doctrine that exploited it. Radar provided information. The Dowding system turned that information into coordinated action. Britain's advantage wasn't that Watson Watt invented radar first. German, American, Soviet, and Japanese scientists all developed radar independently around the same time. Britain's advantage was that Dowding recognized radar's operational potential, invested in infrastructure to exploit it, and developed doctrine that maximized its effectiveness. This required trust between scientists and military commanders that didn't exist in most nations. In Germany, scientific research was compartmentalized, researchers competed for funding, and military officers distrusted civilian scientists. In Britain, Watson Watt worked directly with Fighter Command, attending operational meetings, observing exercises, and refining the technology based on tactical feedback. The Dowding system wasn't a piece of equipment bolted onto existing doctrine. It was a complete reimagining of air defense built around radar's capabilities. The human cost of this institutional difference was measured in thousands of lives. Luftwaffe bomber crews flew missions with casualty rates exceeding 15% per sortie. RAF fighter pilots, guided by radar to optimal intercept positions, achieved kill ratios exceeding 3-to-1. German aircrew who survived being shot down over England were captured. British pilots who bailed out over England returned to duty within days. By October 1940, the Luftwaffe have lost over 1,800 aircraft, nearly 3,000 aircrew killed or captured, and gained nothing. Fighter Command remained operational. London still stood. Invasion was impossible. Hitler turned east toward the Soviet Union, leaving Britain unconquered. Radar won the Battle of Britain not through science fiction ray guns or exotic physics, but through ruthlessly practical application of radio waves to the century-old problem of air defense. The technology worked because the infrastructure existed to exploit it. The infrastructure worked because doctrine maximized its effectiveness. Doctrine worked because commanders trusted scientists to deliver capabilities that matched operational requirements. After the war, Watson-Watt was knighted. Dowding was quietly retired, his defensive strategy vindicated, but his abrasive personality making peacetime command untenable. The chain home stations were gradually decommissioned as more sophisticated systems replaced them. The last operational chain home station closed in 1955. The towers were demolished, scrapped for metal, or left to decay. But the doctrine survived. Every modern air defense system, American, Russian, Chinese, Israeli, is built on principles developed during the Battle of Britain. Detect at maximum range, track continuously, direct interceptors efficiently, engage with overwhelming local superiority. These weren't innovations made possible by radar, they were innovations that radar made practical. Which brings us back to September 15, 1940, and Hugh Dowding standing before the plotting table watching colored markers track German formations across southern England. The markers moved with precision because radar saw them. Fighter squadrons scrambled because controllers assessed the threat. Intercepts succeeded because pilots were directed to optimal positions. The Germans retreated because they couldn't sustain losses against an enemy that could see them coming. Goering didn't understand what he was fighting. He thought he faced pilots and aircraft, numbers and tactics, courage and determination. He was fighting mathematics, detection geometry, intercept vectors, attrition calculations, all made possible by radio waves bouncing off metal. You can't intimidate mathematics. You can't outlast physics. Germany lost the Battle of Britain in 1935 when Britain funded radar research and Germany didn't. The death ray that Harry Grindle Matthews demonstrated in 1924 failed to scale beyond laboratory tricks, but it prompted Harry Wimperis to ask whether electromagnetic energy could detect rather than kill. That question, asked at exactly the right moment by exactly the right person, led directly to Robert Watson-Watt's experiments, chain homes deployment, and Dowding systems development. By the time Luftwaffe bombers crossed the English Channel in 1940, they were already visible to invisible eyes that saw hundreds of miles through darkness and clouds. They were fighting an enemy that could see them long before they arrived, position defenders with mathematical precision, and inflict losses that made victory impossible. The Battle of Britain wasn't won by better aircraft or braver pilots, it was won by mathematics. Radio waves traveling at the speed of light, reflecting off metal objects detected by sensitive receivers, interpreted by trained operators, and used by skilled commanders to position forces with precision impossible without technology. The Germans flew blind, the British could see. In warfare, that difference is everything.